full screen model, right?
Yes.
Okay, thanks for the chair's introduction. So my name is Hongchang Zhou. I'm from Wuhan University of Technology, and actually this work was finished when I work in Japan, the University of Osaka. I work as the assistant professor at that time, and this is a cooperation research work with the Beijing Jiaotong University and the Tsinghua University. And my research title is the predicting fatigue performance of additively manufactured Ti-64 alloy from material to structure scale using Mars scale model simulations. So I will give my talk as the following 4 parts. The first one is our research background. Firstly, from my point of view, I separate the multiple scale phenomenon of the fatigue damage as the 4 scales. The first one is the structure scale, and then is the component scale. And when we focus on the crack tip, we can find the grain scale fracture. And finally is the atomic scales, right? So although we can understand that the simulation or the phenomenon of the fatigue or fracture is the most accuracy by using the atomic scale analysis. However, there's a question to predict the fatigue life of the structure scale components. Is it possible to solve this problem effectively on such a small scale? I mean, can we use the atomic scale simulation to predict the fatigue life of the structure scale? So some researchers perform the molecular dynamical simulation by using this tiny small model. You can see the size is only 20 nanometer. So to finish this simulation, the calculation time is like this. This is countless. So it is impossible to finish the simulation based on the atomic scale. Therefore, the appropriate length scale setting is necessary to achieve the Mars scale simulation. And we think that only the simplest factors that are sufficient to achieve quantitatively predictions for fatigue performance is most important. Therefore, we skipped the atomic scale simulation, and our Mars scale model is from the grain scale to component scale. Finally, we can reflect the fatigue performance of the structure scale model. And we think it is necessary to propose an applicable Mars scale model for predicting the fatigue strength of alloys with high accuracy and efficiency. So the highlight of this sentence is the applicable model and high accuracy and efficiency. And this is our previously proposed Mars scale model. The input data of this model is very simple, only the test condition and the tensor property and the microstructure information. And there are 3 submodels. The first submodel is a macroscopic finite elements analysis model. And in this model, it works as the crack driving force. And the submodel 2 is the microstructure model. This model acts as the crack resistance. And based on the information from the submodel 1 and the submodel 2, we can go to the submodel 3, which uses the crack and the grain boundary interaction theory. Based on this theory, we can calculate the crack growth rate, and finally we can calculate fatigue life. And output date of this model is the SN curve. So we can find the good agreement between the simulation result and the experiment ones. And in our previous research, we try use the different type of steel, 3 type of steel and 4 type of specimens. We use the smooth specimen and the notch specimen, especially the dual notch and the sharp notch, and also the tensor specimen with the notch. So we obtained the various experimental results, the different SN curve for the different materials, and the simulation results of our Mars scale model show a good agreement with the experimental ones. And we also published many journal papers on the International Journal of Mechanical Science and the Material Design and the International Journal of Fatigue. However, in our previous research, we focus on the wet joint and various steel. And so this is a very common steel and very common specimens. In this, we can find for the steel or the low carbon steel, the microstructure is very easy to be modeled. Sometimes, or the most researchers will model this microstructure, the grain as the circle or the ellipse. However, for the additive manufactured Pi 64, this kind of alloy, it has the more complicated microstructure, and the grain orientation and misorientation can be different from those with the low-grade steel. And the question is that, can we make this equivalent shape of the grain as a circle or ellipse? So we need to think what is the key parameters dominating the fatigue crack initiation and growth. Therefore, our research motivation is to develop a general method to characterize the microstructure features on the fatigue strength, which can be applied to AM Ti 64 alloy. And then I will introduce the detail of our mass-scale modeling strategy. The first submodel, this is our outline of our mass-scale model. The first one is the macroscopic finite element analysis model. So the goal of submodel 1 is to calculate the relative elastic and plastic strain tensor and to define the active zone. And we can use the empirical formula proposed by Lee, this one, to calculate the cyclical stress-strain relationship. And based on this kind of SS relationship, we can perform the FEM simulation to obtain the stress and strain distribution of the specimens. And also we define the active zone as the area which is the crack will be initiated in this small area. And then we will go to the submodel 2. Submodel 2 is the goal is to define the spatial distribution of the microstructure on the surface plane and the inside plane. Firstly, I will introduce about the surface plane modeling process. And firstly, the date based on the general, we need to obtain the microstructure information through the EBSD results. Here, I show the grain map from the EBSD, and then we make the model of the grain as the ellipse. And we obtain the key parameter of the grain is the major and minor axis length, and the major axis angle, and the unit angle of this grain. And then we use the Monte methods to obtain the surface grain distribution. And the next step is to define the microstructural distribution in the inside plane. And firstly, we need to understand the key parameter dominates the fatigue crack initiation and growth. Firstly, we use the basic theory, which is proposed by Professor Tanaka. That is the interaction theory between the crack and the grain boundary. So in this theory, we can find the relationship between the crack tip and the grain boundary, and we will calculate the dislocation density based on this distance. So therefore, when we check the crack growth in the inside plane in like this process, we will focus on the crack front. And now we will focus on the relationship between the crack front and the grain. So we care about the distance between the crack front and the grain boundary. And this is the very important parameter, that the distance between the crack front and the grain boundary is more precise than the average grain size. As I introduced before, most researchers will model the grain as the ellipse or the circle. However, that kind of parameter, like the equivalent diameter of the circle, is not as good as precise as this kind of distance. And therefore, the key parameter of the grain boundary effect can be reflected as two parts. The first one is the distance between the grain boundary, and the second one is the grain misorientation. And based on this kind of concept, we will build the microstructure distribution in the inside plane. So I will not go to detail about how we modeled of the microstructure. However, the most important concept is that we obtain the microstructure distribution and define the equivalent grain boundary length, Li, and also we define the orientation and misorientation with the adjacent grain. So that is our model for the inside plane. And the last one is the crack growth model. And we use the interaction theory between a crack and the grain boundary. And this theory is proposed by Professor Tanaka at 1986. And in this model, we need to calculate steepness C and the crack tip sliding displacement delta CTSD. And based on the delta CTSD, we will calculate the crack growth rate, DADN. Finally, the fatigue life can be calculated as here. And the input data of this model is very simple. We only need to get the grain size and the friction strength to move this location, and the effective shear stress. And the output data of this model is dislocation density ahead of the crack tip, and the slip bend C, and the delta CTSD, and also the DADN. And finally, we can obtain the fatigue life NF. And the very important parameter of this model is the crack driving force. That is the effective shear stress. So we show the procedure how to obtain this parameter. So firstly, we need to obtain the equivalent stress tensor from the FE analysis. And then we make the model considering the crack shape transition from the stage 1 and stage 2. And also based on the equivalent K, that is the stress intensity factor, to consider the equivalent effect of the crack tip and the remote stress distribution. And finally, we can calculate the delta tau, that is the effective shear stress range, considering the slip system of the HCP crystal. So HCP crystal is especially considering for the Ti64 for this kind of material. And this is the evaluation of the fatigue life, the procedure for that. Firstly, we assume the crack initiation from the all grain assigned in the active zone. So, for example, if there are thousands of grain on the surface, we will produce this procedure for 1,000 times. And we then, to calculate the delta tau, that is the driving force for the adjacent grain, and to calculate the average delta tau divided by the tau F, that is the crack driving force divided by the crack resistant force. And finally, we can make this simple model. Actually, this is the 1D model based on the interaction theory between the crack and the grain boundary. So from this procedure, we can calculate the crack growth rate. And finally, to get the number of cycles to failure for each grain. And we will use the weakly sneak principle to calculate the fatigue life by using the minimum number of cycles to failure from all the crack interior sites. And now I will show the model foundation. And we use the SLM technology to build a material of the AM titanium alloy. And this is the microstructural information. And also we can see some micro defects. And we perform the, machine two types of specimens. One is the material level, that is the carbon. Another one is the structure level, which means the specimen size is much larger, and that is the traction rod, which will be using the railway components. And here we obtain the number of the SN curve. And we use this is the crack growth rate calculation formula. Very important part is that we need to identify this parameter Cn and that CTSD threshold. Firstly, that is very similar with Paris law. The material constants should be identified first. Therefore, we perform the fatigue test by using the steel A. Steel A is a type of the ferro and pearl steel, so we can use any type of steel to identify this parameter. And then we fit in the simulation results with the experiment 1 and obtain these 3 parameters. And then by using this identified parameter, we try to predict the fatigue life of the material level. So we can see a good agreement between our prediction results. And also we obtain the structure levels SN curve. And this is our prediction results. So we can find the model was validated using the SN data from the both material and structure levels, showing the excellent correction between the prediction and the experimental results. And also we try another kind of simulation that we consider the model with defect and without defect. So the blue marks show the results considering the defects. So we can find the shorter fatigue life compared with the experiment 1. And now I will show you the strategy for considering the defect. We use the virtual crack concept to considering the effect of the defect. Firstly, to simplify the defect as the semi-ellipse, and we assume this semi-ellipse as the virtual crack, and the fatigue life in this red region will consumed in the virtual crack, and the fatigue life in this green region is the remaining fatigue life. And this part is the fatigue life that considering the effect of the defect. So that is our strategy to considering how to simplify the defect of the influence of defect. And this is a summary of our research. And I will not go to the detail of this one, but very important is that we performed the strict validation using the experiments with the 3 types of steel and the 3 types of specimens. And we proposed the mass-scale analysis framework that integrates the microstructure, the material, and the structure information, which offer a basis for the accurate prediction and the design of the fatigue-resistant AM components. So that's all for my presentation. So thank you for everyone.